Dear students, good morning to one and all. In your previous session, we have discussed about the conversion of data types, which is contains more mathematical form calculations. Hope you understood it well. If not, again you listen it carefully till you get a clear picture about the conversion of numbers. And already I posted an assignment in your WhatsApp group to do the conversions, and as early as possible you complete that assignment and mail to me, so which carries some marks for your internal examinations also. So now today's session we are going to discuss about the complements, the second topic of your data representation, complements. So what do you mean by these complements and why we use them if you discuss? As it is shown in the slide, complements are used in digital computers for simplifying the subtractions and logical manipulations. So here I am using a word called subtraction. What does it mean? Why not bothered about the additions? So additions and subtractions are the basic operations in an arithmetic system. So, see, if you want to perform addition, it will be very easy because two signs will be same and you will get a positive value. But when you consider the subtraction concept, two values, if you consider those two values, sometimes if the two positive values are there, subtracting is different. But one value is positive, one value is negative, subtracting is different. So, here greater value can be subtracted from lesser, and lesser value sometimes can be subtracted from greater value. So there is no guarantee that every time you will get a positive result only. So when you are performing a subtraction, sometimes you make it a negative value also as a result. Say for example 3 minus 9. If you want to perform the operation 3 minus 9, the result will be minus 6. So in computer, as it is represented, able to understand only zeros and ones in the form of bits. So how can you represent a negative number in the computer? That is a major problem here. So to avoid that problem and to easily understand by the computer the negative numbers also, we perform these arithmetic operations like addition and subtraction using the concept of complements. That is the complements and its uses. So what are the types of complements? So as it is shown in the slide, there are basically two types of complements are there. One is R's complement and R minus 1's complement. Here, what is R? We have already discussed the significance of R in the previous session. R stands for radix. It is nothing but the base of the number system. So as you know, there are basically four number systems we have discussed like binary, decimal, octal and hexadecimal. Binary base is 2, decimal base is 10, octal is 8, hexadecimal is 10. So for today's session, we don't much bother about the octal and hexadecimals. Let us consider and concentrate on binary complements and decimal complements. So as binary base is 2, so in binary complements we will have 2's complement and 1's complement. And decimal base is 10. In decimal complements, we have 10's complements and 9's complements. But how to achieve these 9's complements and 10's complements for decimal or 1's complement and 2's complement for binary? See, you see in the slide it is given R minus 1 complement you will achieve by subtracting each digit of a number from R minus 1. What does it mean? Say for example, if you consider a decimal number, the decimal base is 10, R minus 1. So 10 minus 1 you will get a 9. So whatever the digits are given in the decimal number, each digit must be subtracted from the value 9. Then you will get 9's complement. In the binary system, R minus 1 means 1's complement. So each digit of the binary number you have to subtract from 1. Then you will get the 1's complement of a binary number. Then what about R's complement? So as it is shown in the slide again, so if you add 1 to the lower order digit of the R minus 1's complement, you will get R's complement. That R's complement may be 10's complement or 2's complement. It depends upon the base. So if you see the example, you will get a clarification how to calculate r minus 1 complement and r's complement. You see this here I have given example for 9s, 10s complements and 1s and 2s complements also. You take a value 835 to calculate 9s and 10s complements. 835, it contains 3 digits, 8, 3 and 5. So we have to subtract each digit from r minus 1. Here r is base 10. R is base 10. So r minus 1 is 9. So all the 3 digits of the given decimal number are subtracted from 3 9s. Then if you subtract 830 from 999, you will get 164. So here 164 is the 9th complement of 835. Then what is its 10th complement? So r's complement. So r's complement of 835. How you get r's complement if you have r minus 1? Simply by adding 1 to the lowermost bit. Here in the above example, the lowermost bit for 9th complement is 4. In the 164, the lowermost bit is 4. That's why if you add 1 to that, you will get 165 as 10th complement. This is the way how you calculate r's complement and r minus 1 complement in the decimal system. Let us consider one binary value also. You take 1010 base 2 binary number and it contains 4 digits. That's why we have to subtract from 4 ones to get the ones complement. So after subtracting 4 ones, 1010 from 4 ones, you will get 0101 as the ones complement. You see in this simple logic, what is the original number given? 1010. Yes? After calculating the first ones complement, what the result you got? 0101. Did you observe any logic here? See, this 1010, when you change the positions, ones as zeros and zeros as ones, you will get the ones complement. See, 1010, wherever ones are there, you put zeros, and wherever zeros are there, you put ones. It is nothing but your ones complement. So, simply toggling the bits means zeros and ones are changed as ones and zeros, you will get the ones complement. And again, as I told you, 2's complement is nothing but adding 1 to the lowermost bit. Here 0101 gets added with 1, so you will get 0110. 0110 as the 2's complement. This is the way how you calculate r's complement and r minus 1's complement for any number. You can ask me, sir, in the data types we have discussed hexadecimal and octal also, but why you are not bothering or not considering those here? It's very simple. Same logic you can apply over there. If you take hexadecimal, 16 is the base. If you want r minus 1's complement, you need to subtract every value from 15. Yes or no? Every value from 15 you have to subtract, and whatever the result you get, if you add 1 to that, you will get 16's complement. In the same way, 8's complement, you can subtract each digit from 7, means r minus 1, and then after getting the r minus 1, that is 7's complement, if you want to get r's complement, that is 8's complement, add 1 to the given resultant number, then you will get 8's complement. So that's why whatever the logic and whatever the calculations we are performing for base 10 and base 2, the same are applicable for even any other base system like your octal and hexadecimal. So now there is one more procedure for calculating r minus 1's complement here. Previously we have simply discussed an easiest way, subtracting from r minus 1, each digit subtracting from r minus 1. But in a scientific scientific way, for calculating r minus 1's complement of any number n, you just use this formula as r power small n minus 1 minus capital N. Here what is r? Base or radix. What is small n? Given there, small n stands for the number of digits in the given number. So in the previous example, 835, there are 3 digits. So small n is equal to 3. And what is capital N? The actual number, 835 or whatever it is. See, simple. Here, by using that formula, I am going to calculate r minus 1 by taking one example. See here, an example I have taken is 546700. 9th complement I want for 546700. So here the original number is 546700. So if you substitute this in the above formula, here for this the base value is 10, the radix value is 10. So 10 power n. What is n? How many digits are there? 6 digits are there. So 10 power 6. What you are getting over there is represented. So 10 power 6 minus 1. In the above formula, we have given minus 1 minus original number. Again, you are going to back same from 6 nines minus 546700. Same. But this is the scientific way. So that is very easy to remember, subtracting each digit from 999. But why we need to subtract each digit from 999? From where we got it? For that, this is the explanatory part. In scientifically, if you want to calculate r minus 1 complement, you have to use this formula, that is r power n minus 1 minus capital N. Capital N stands for the original number. So you will get 45329 as the original number. So that is, this is r minus 1. Once if you get r minus 1's complement, getting r's complement is very easy. Adding 1 to the last digit, that is last digit in the r minus 1 is 9. So if you add 1 to the 453299, you will get the r's complement. This is one way of calculating the r minus 1 complement also. So, but is it same applicable for binary also? Same formula? Yes, obviously. Same formula is applicable for binary also. So you take example for binary. Binary also same. Here base will change. There for decimal, if the base is 10, for binary the base is 2. So 2 power n, that is small n, stands for number of digits minus 1. After calculating 2 power n minus 1, then whatever the result you will get, you subtract capital N. Capital N here is original number. So you take 1011001 as original number. So how many digits are there in that? 7 digits are there. So small n value is 7 here, and capital N is 1011001. 2 power n we need to calculate. So 2 power 7. So what is 2 power 7? It is 128. But 128 is a binary number? No, there is no binary values as 128. So that's why, so by considering this 128 as a decimal value, you have to convert it to its binary equivalent. See, in the side table, I have given you how to convert a binary decimal number into binary value. You know this procedure already we have discussed in the previous class. 128 is divided by 2, 64, 0 is remainder, again divide 0 remainder, till you will get the quotient as 0. You will repeat the process and you will write the remainders from bottom to top. You write the remainders from bottom to top. You will get the result as 2 power n as 170. So if you get 2 power n as 170, you have to subtract 1, because the formula is saying you 2 power n minus 1. Then you will get all 7 ones. What I told you in the previous slide is that same only. If n number of digits are there, you subtract each digit from 1 to get r minus 1's complement. Again, we are getting the same but with a scientific manner by using a specific formula. So after subtracting the given value from all ones, you will get 0, 1, 0, 0, 1, 1, 0 as the final result for r minus 1. Again, you see the bits are toggled. So the original number is 10, 11, 001. The r minus 1 complement is wherever 1 is there, you put 0, 0, and wherever zeros are there, you put 1. So 0, 1, 0, 0, 1, 1, 0. Same toggling, changing, altering zeros and ones, you will get the r minus 1's complement. Then you know how to get r's complement. Simply adding a 1 to the last bit, you will get a R's complement. This is another way of calculating R minus 1's complement and R's complements in a scientific manner. So, in the examination, if they give you to calculate R's and R minus 1's complement, you can follow the previous one, but you have to just simply mention this formula the way how you need to calculate, then you will get full marks. If you don't mention this formula, you may not get full marks. Only just for procedure, only half marks or 50% marks only you will be awarded. Okay. Then next, the R's complement of n digit number n, bases are defined as r power n minus n. Just now we have discussed there r power n minus 1 is there, no. So for that minus 1, if you add 1, that will be discarded. In the previous formula for r minus 1, the formula given is r power n minus 1 and minus capital N. So now if you want to calculate R's complement, as you need to add plus 1, then that minus 1 and plus 1 gets cancelled, and the formula you get is R power n minus capital N. So you take another example here to calculate R's complement. So 10's complement of 2389 is 9999 minus 2389 plus 1. I told you plus 1 you need to add. So 7611. So here 10 is the base, that is radix, and n is 4, there are 4 digits. So R power n is equal to 10 power 4, you will get 10,000. So here R power n minus n, 10,000 minus 2389, you will get as 7611. Similarly, the same formula also applicable to binary values, then you will get 2's complement for the given number in the same fashion. Okay. Now, as we discussed in the first slide of this complements itself, these complements are basically used to simplify the concept of subtractions. Why the concept of subtractions means sometimes in the result of the subtraction you will get negative values where our digital computer is not having any specific procedure for representing negatives. That's why by using the complements, the most significant bit of the result will be put as 1. The most significant bit of the result will be put as 1 as a representation of the negative. So you just see the subtraction of unsigned n digit numbers, that is m minus n. So definitely you know very well that you need 2 values for subtraction, m and n. So how you perform this m minus n using the complements method? You see in the second line, add m to the R's complement of n. So because there is no concept of subtractions in the computers, so we are using additions. So you have to calculate R's complement of n. So how you calculate R's complement of n? By using the formula r power n minus n. That is the R's complement of n. So whatever you get r power n minus n, you add that to m. So that result is nothing but m minus n plus r power n if m is greater than or equal to n. Then the sum will produce an end carry r power n, which is discarded. Why end carry is generated? If base 10 is there, 10 to the power of 4, you will get 10,000. So, but here the value digits in m and n are only 4 digits. But 10 power 4, what you get? 10,000. So 5 digits you will get. So the 5th digit is considered as carry and you need to discard it. You don't bother about that carry if m is greater than or equal to n. M is greater than or equal to n. Please remember this. When you discard carry, if the m value is higher than n value, then whatever the carry you will get in the sum, that you can simply discard. But in the second case, if m is less than n, the sum does not produce any end carry and is equal to r power n minus m, which is the R's complement of n minus m. R's complement of n minus m. So n minus m, you will get one value. If you subtract that from r power n, you will get R's complement only. So to obtain the answer in familiar form, take the R's complement of the sum and place a negative sign in front. So how you perform these subtractions using unsigned values, we'll see with the example. You see here, I have taken an example. M value is 72,532, N value is 13,250. This is first case 1, M is greater than N. So here the actual result what you get is 59,282, which is a positive value. So how I told you to perform? First you have to find out the tens complement of the N. As per the previous procedure shown here, if you want to perform the subtraction, you need to calculate R power n minus n. R power n minus n means the 10th complement of n, base whatever it is. If it is a binary system, the 2's complement of n. Because now we have taken the example in the decimal form, so 10th complement of n you have to take. How you get 10th complement of n? So all 9's you have to subtract there or there, and then you need to add 1 to it. So if you subtract 13250 from all 9's and adding 1 to the result, you will get 86750 as 10's complement. But 86749 actually you will get the result, that is 9's complement. But what we want here is 10's complement. So that's why after calculating the 9's complement as per the procedure, that is subtracting 13250 from all 9's, you will get 86749, but you require 10's complement, that's why we have to add 1 to the last bit. So 10's complement of n is 86750. So you have to add these two numbers, you will get 1,59,282. I told you you will definitely get a carry bit if m value is greater than n. Yes, you will get a carry bit. So you need to discard the carry. The last bit whatever you got 1, that is carry bit, and in the case of m is greater than n, you have to discard the carry. So the answer is 59282. 59282. You can ask me, sir, for performing simple subtraction, do we need all this confusing procedure? See, you are learning how to perform subtractions from the beginning. But see, in the computer, inside the computer, the subtraction operation is performed in this procedure only. That's why, as we are going to know about all the basic organization of the computers, we have to know how each and every operation inside the computer is being performed. That's why we are going to learn this. Otherwise, simple your decimal number systems, how you subtracted from maybe first class onwards, you know how to do subtractions with carry and without carry, all these things. So that is, you keep it aside. That is for your normal information. But inside the computer, the subtraction of two numbers is being done in this procedure only. So now, in the second case, you take the m value is less than n. The same two numbers in the above I have taken in the reverse way. So here m is 13,250 and n is 72,532. So what you have to get the result? The same quotient is equal. That is number 59,282, but its sign should be negative. Its sign should be negative because m is less than n. So for this also, you add m and n by taking 10's complement of n. So m is 13,250 and 10's complement of n here is 27,468. 27,468 means if you calculate the 9's complement of n, that is subtracting 2,532 from 99999, you will get 27,467, but to get the 10's complement, you have to add 1. Then, after getting the 10's complement of n, as per the previous procedure, you have to add both the values, that is m value with the 10's complement of n. So after adding these two values, you get a sum of 40718, which is equal to 40,718. Do you got any carry here? No. In the previous example, because m is greater than n, you got carry. But in this example, m is less than n, there is no carry is generated. So if no carry is generated, what is the procedure we have to do? We have to convert the result into tens complement. Yes, that's what I told you procedure. So if no carry is generated, then you have to consider its tens complement as a final result C, which is the R's complement of n. So if does not produce an end carry, and is equal to tens complement of the result. So here in the second example, where m is less than n, for the sum 40,718, no carry is generated, we have to convert that sum into its tens complement and put negative sign as the final answer. So the tens complement is 59,282 and with a negative symbol. So that is the final result. So this is the way how a subtraction operation is being performed inside the computer. Then this is in decimal number system. And what about the binary? Let us see in the next one. So as an example, x is equal to 1010100 and y is equal to 14011. So calculation of x minus y. So same, there how you calculate tens complement for y. Here you calculate 2's complement for y. So what is 2's complement for y? First you need to convert 1's complement, means all the 1's will be converted into zeros and all the zeros will be converted to 1's. In the above example, so y is equal to 1, 4 zeros and 2 1's. Its 1's complement is 0, 4 1's and 2 zeros. 0, 4 1's and 2 zeros. But I told you it is 2's complement. So if you want to get the 2's complement, you need to add 1 at end. So that's why here the 2's complement of y is equal to 0, 1, 1, 1, 1, 0, 1. And you need to add these two. So what you are adding? Not x and y. You are adding x plus 2's complement of y. After you perform this addition, you get a sum with a carry value. A carry means, so here both x and y are 7-digit numbers. The result you get is 8-digit number. So that 8th digit, the most significant bit, is considered as a carry. So when you generate a carry, you have to discard the carry for getting the result. So after discarding the carry, the answer is 0010001. That is x minus y. Here simply you can say that there in the decimal system, it is very easy which one is greater and which one is smaller number. But here obviously I can tell you that x is greater than y because there is an end carry is generated in the calculation of the procedure. So now we will calculate y minus x, where y is lesser number and x is greater number. So y is equal to 1, 000011. So you consider 2's complement of x. 2's complement means first find out 1's complement by altering all the zeros and ones each other and add 1 to it. So after calculating the 2's complement, you will get 0, 1, 0, 1, 1, 0, and you need to add both. The result is 1, 1, 0, 1, 1, 1. You have no end carry generated here in the addition. What is the procedure you have to follow if no end carry is generated? If no end carry is generated, then whatever the result you obtained, for that you have to calculate 2's complement. So the result here is 1, 1, 0, 1, 1, 1. For it to calculate a 2's complement, first you go for the 1's complement. That is 001, 0000. That is the 1's complement of the sum. Okay. So after calculating 1's complement, you have to add 1 to the last bit. Then that is the answer. But you don't forget putting minus symbol in the beginning. So because here y is a smaller number and x is a larger number, the result you will get obviously is a negative value. So minus 0010001 is the result, which is obtained by calculating the 2's complement of your end sum and putting the negative sign in front. So this is the way how you perform subtractions in the complements form. So either it may be a decimal system or it may be a binary system or whatever, even octal and hexadecimal, also the same procedure you need to follow. So this subtraction of these two signed two's complement number is summarized here. Whatever the procedure we have followed in the previous slide, I have briefly summarized the total concept here. That is, first you take the two's complement form of the subtrahend. In the previous example, the subtrahend in the first example is y and in the second example is x. So you take the two's complement form of the subtrahend. Don't get confused. So that example, see, actually this calculation parts, all these things, if you can explain on the board in the classroom, then it will be a little bit easy for you. But it is very unfortunate that we need to carry on everything through online classes. That's why you need to work more hard than listening the regular classes. That's why I am again briefly summarizing to avoid the confusion in the calculation part. So subtraction of two signed two's complement numbers is given as follows. The subtrahend, maybe it is x, y, z or whatever it is, the second number. Subtrahend means the second number. What you are going to subtract? What you are going to subtract, that is subtrahend. You take the two's complement form of that number. Okay, and add that number to main hand. Add that number to the first number. So first number is added to the two's complement of the second number. If you are again confused what is main hand, what is subtrahend, because you might have learned these words long back, maybe in the high school section or so. That's why don't worry. You take the first number, second number. You are going to subtract the second number from first one. Now the procedure for that is you first calculate the two's complement of second number and add that to the first number. So if a carry is generated, you discard it. If a carry is generated, you discard it. If no carry is generated, then you have to calculate the two's complement of the resultant value with a negative sign, then that is called as a final result. I am repeating again. If a carry is generated, simply discard it and that will be the final result. No negative sign will be there because the first value is greater than the second value. But in the second case, if the first value is less than the second value, then no carry is generated. In this procedure, no carry is generated. Then what to do? If there is no carry generated over there, simply you have to find out the two's complement of that temporary sum, and whatever the two's complement you got, for that you put a minus symbol, that will be your final result. So this carry. So you can say carry. In the concept of additions, we will get a carry. But here in the technical word, in the digital computer knowledge, this carry is termed as a overflow. This carry is termed or named as a overflow. So here, if an overflow occurs when two numbers of n digits each are added and the sum occupies n plus 1. Why we need to discard this carry, sir? That carry will be used as a sign number. But you see, when you are going to perform addition of two 8-bit numbers or two 4-bit numbers, as I told you, one of the components of your CPU is registers. In the first class itself I told you, I don't know whether you remember it or not. If not, you just go back to the first class notes or the PPTs what you have downloaded, videos. I told you a CPU contains arithmetic unit, logical unit and also some registers that are being used for temporary storage purpose and calculations. So you should take two 8-bit registers to perform addition of two 8-bit numbers. When you are going to perform addition of two 8-bit numbers, sometimes definitely you will get a carry. Okay, if see for example 24, a 2-digit number in the decimals, and 36 is a 2-digit number, and if you are adding 24 to 36, the result is 60. You get only 2-digit value. But sometimes if you are adding the 24 to 92, say let's assume, if you are adding 24 to 92, what you get is 116. Two 2-digit numbers are added and the result you got is 3 digits. The third digit is a overflow or it is a considered as a carry. But 2 registers are only 2-bit registers. The resultant register also 2-bit register. So how the 2-bit register will store the carry? It cannot store the carry. So it simply discards the carry. But our result is wrong you will get. Yes. So actually if you add 24 to 92, you should get 116 as a result. But because of this concept of overflow, the register cannot store 3 digits. Simply you will get 16 only. 16 is the right answer of adding 24 to 92? No. 116 is the right answer. So where is this one? So that concept is here considered called as overflow. So these overflows are problems since the width of the register is finite. Width of the register is finite. Therefore, to overcome this concept, there is a flag is set. A flag means whenever such a overflow appears in the calculation part, a flag is set to 1. So there is a special register in your computer called as a flag register. So for flag register, carry bit, overflow bit, 0 bit, negative bit, like that, there is a flag register with 8 bits or 16 bits, depends upon the length of a computer or length of a bus or whatever it is. So in that flag register, 1 bit will be there that specifies the carry or the overflow value. That will be set to 1. So if it is set to 1, means whatever the result you got 16, for that you have to add the carry bit as a final result 116. So here, whenever the overflow occurs, the computer uses a special register called as flag register. This, if you have 2-bit answers or if you go to any interviews there or in the final examination, sometimes in the Viva questions or whatever it is, definitely this is an important concept. If a overflow occurs because of the restricted length of the registers, how this problem will be overcome with the help of a flag register. So this is the way how you solve the problem of overflowing the final result. So this detection of the overflow depends on the number of signed or unsigned values. Yes or no? Number of signed or unsigned values. For unsigned numbers, an overflow is detected from the end carry. As I told, 2 plus numbers are there. 2 plus numbers are there means, just now example 24, 92. End carry will be the overflow. Yes or no? But when you go for the signed numbers, signed means when you are performing addition and subtraction, the 2 values may be positives or 2 values may be negatives or 1 is positive, 1 is negative, many things may happen. So at that situation, how this overflow will be considered and measured. For addition of signed numbers, an overflow cannot occur if 1 is positive and 1 is negative. Yes? Both have to have the same sign. So an overflow can be detected if the carry into the sign bit position and the carry out of the sign bit position are not equal. So if both carry in the sign bit and carry and out of the sign bit, if both are not equal, then only overflow will be generated. Means if one is positive, another one is negative, then definitely a overflow occurs. Okay, that's why this is the way how a overflow is generated and is rectified with the help of a flag register. So my dear students, arithmetic addition how is performed by using this again concept. So the addition of two numbers in sign magnitude form follows the rules of ordinary arithmetic. Simple. However you are performing the arithmetic till now, the same format you can follow for the arithmetic addition. If the signs are same, we add two magnitudes and give the sum with the common sign. So plus plus, the result value also plus. But if the two numbers are in minus minus, add the two magnitudes, the result will be minus. See for example, minus 24 minus 36. The result is minus 60. How you got here? Minus symbol is common and 24 plus 36 is 60. So you don't find any problem in adding two signed magnitude numbers with the same signs. Two numbers of positive, no problem. two numbers of negative, no problem. But one number is positive, one number is negative, then how you are going to perform this addition. So if the signs are different, what we do in the previous one, we subtract the smaller magnitude from the larger and give the result with the sign of larger magnitude. So in the previous example, in the given example here, plus 25 minus 37, two values. We are going to perform addition. Here, addition between two different signs. 125 sign is plus, 37 sign is minus. When you perform this addition, here the larger magnitude is 37, smaller magnitude is 25. So you subtract the smaller magnitude from the larger one. So 37 minus 25, the result is 12, and you have to put the sign of the larger magnitude. So the sign of the larger magnitude is minus, that's why you will get minus 12. This process requires comparison of signs and magnitudes and the performing either addition or subtraction. So even arithmetic addition also, if two signs are not equal, we are going to use the concept of subtraction. But to perform this subtraction, again you need to go for r's complement, r minus 1's complement, whatever in the previous slides we have discussed. You have to follow the same procedure for subtraction. So this is the arithmetic addition of two same sign numbers and two different sign numbers. Okay, so this is ends with your complements session. So again, you go to Google or whatever it is, you get more number of complement examples and you try to solve those, and whatever the result you got and what is the result given there, both are equal or not, you just check out. Then definitely you will better understand this class. Okay, my dear students, this computer organization is of more calculative basis. That's why once again my humble request is to listen this slides or this video more and more times till you get understood every topic by downloading it. If you have any problem, again you are requested to WhatsApp or mail. Till now I have not received any queries about my previous 3 sessions or 4 sessions. Thank you one and all.